What's up, everybody? Welcome to another video. Hope you're ready to flex those brain muscles. Over the next couple weeks, I'm going to spend some time building up my college algebra playlist. So in this video, we're going to look at solving rational equations like this example here. So if you aren't familiar at all with solving equations involving fractions, I'll link a video above right now. Please go click that. The general approach we use to solve equations involving fractions is that we try as quickly as possible to get rid of all the fractions. And typically what we do is we find the least common denominator and multiply both sides of the equation by that least common denominator, and that allows us to get rid of all the fractions. It's a beautiful thing, and it's no different when we have rational equations. Even when we get polynomials and variable expressions and denominators, we still want to get rid of the fractions as quickly as possible to make our lives easier, and we still do that using the least common denominator. So that's going to be the first thing we're going to do when solving rational equations is find the least common denominator and multiply both sides of the equation by that least common denominator. So I have a method that I use, which is I rewrite the entire equation where the denominators are fully factored. So this 3x is already fully factored, okay? But this 4 can be written as 2 squared. So anytime there are integer values in the denominator, I want to write them as a product of prime numbers, right? So 2 times 2 or 2 squared. Similarly with 6x, I can write this as 3 times 2 times x. So that would be the fully factored form of 6x. I took the integer and broke it down into a product of primes, and the x I left alone because that can't be broken down any further. And then this 3 is already prime, so it's just going to stay 3. So the reason why I do this is because this makes it really easy to find the least common denominator. What we do now is we identify all of the unique factors across all of the denominators. So we have a 2, a 3, and an x. So I'm going to write those out here, 2, 3, and x. Now we look at what is the largest number of times each of these factors appears in a single denominator. So this 2, for example, 0 times in this denominator, 2 times here, 1 time here, 0 times here. So the largest is 2, so we're going to write 2 to the power of 2. Okay, what about 3? Well, we have 1, 0, 1, 1. So we're going to write a 1 here. What about x? Well, we have 1, 0, 1, 0. So we're going to write a 1 here. The product of 2, 2, 3, and x is our least common denominator, which is 2 times 2 is 4 times 3, that's 12, 12x, okay? So we found our least common denominator, which, by the way, is just the least common multiple of all the denominators. So now what we can do is 2 different things. We can go back to the original equation, multiply both sides by 12x, and do some simplifying from there. Or we can use this factored, fully factored version of 12x and look at this equation here, which is the same thing as this original equation, and multiply both sides of this equation by this fully factored form of 12x. Either way works. I find that the second way is a little easier. It involves less writing. Hopefully you'll see what I mean, and it's especially easier once we get into more complicated equations. But I'll show you exactly what I mean here. Once I get a marker that works, let's try this blue one. So we're going to multiply both sides of this equation by 12x, but in this case I'm going to use this form, 2 squared times 3 times x. So both sides, all 4 of these terms, we're going to multiply by 2 squared times 3 times x, which again is 12x, okay? Multiplying both sides of the equation by the least common denominator. And again, equivalently, you could go back to the original equation and multiply both sides by 12x. I think it's a little more work because once we multiply both sides by the fully factored form and all our denominators are fully factored, we can visually see what's going to cancel and what we're going to be left with, right? Because 2 squared times 3 times x, we can think of this as being over 1, okay? So when we multiply this into each term, all of these terms are going to end up in the numerator. So stuff's going to cancel. And in this case, what's going to cancel? A 3 and an x. A 3 and an x. So we're going to be left with this 2, which is already in the equation, this 2, as well as 2 squared because the 3 and the x canceled. So when we multiply that in, the 3 and the x canceled, the denominator is gone, right? So we have 2 and a 2 squared left. Hopefully you see that. Hopefully that makes sense. If you need to write it all out, go ahead and do that. But hopefully you're following what I'm doing here. This 2 squared is going to cancel, and we're going to be left with 1 times 3 times x. This 11 is going to hang out, but look what's going to cancel. A 3, a 2, and an x. 3, 2, and x, we're going to be left with one factor of 2. So this is going to be 11 times 2 minus just 1 3 is going to cancel here. So we're going to have 2 squared times x. Now we can write this. We can start multiplying stuff out, right? We don't have to keep it in factor form anymore because now we just have, it looks like it's going to be a linear equation that we could solve. So 2 times 2 squared, that's going to give us 8 plus 3x, we can just leave that alone for now, equals 11 times 2, that's 22, minus 2 squared times x, that's 4x. And we do have now a simple linear equation that we can solve for x and then go back and check our solution and make sure that it's correct. So really this is the meat of the work when it comes to solving rational equations, is finding that least common denominator and multiplying both sides by it and simplifying and making sure not to make any little silly mistakes, okay? So once we get to this, now we can solve. I'm going to add 4x to both sides, plus 4x plus 4x. So these here are going to cancel, right? We're going to be left with 7x. So I have 8 plus 7x equals 22. Now I can subtract 8 from both sides. And what we get is 7x equals 14. And when we divide both sides by 2, we are going to get x equals 2. Now we go back and check this into our original equation. When we substitute 2 into the original equation, does it satisfy the equation? Meaning, does it leave us with a true statement like 2 equals 2, for example? In this case, it does. I'll leave you to check that on your own. But it's going to be really important that when we're solving these rational equations that we always check our answers. And I'm going to talk about why that's the case right now. So again, what we want to do when we're solving these rational equations is get rid of all the fractions by multiplying both sides of the equation by the least common denominator. What usually happens with rational equations is that least common denominator involves a variable. So in our last example, it was 12x, where x is the variable, and we multiply both sides of the equation by 12x to clear out all the fractions. So what happens when we multiply both sides of an equation by a variable expression? Well, we potentially introduce additional solutions, which we call extraneous solutions. So these are new solutions that are not solutions to the original equation. So here's an example. We have this very simple equation, x equals 1, which has one solution, 1, right? When we multiply both sides of this equation by x is a variable expression, right? So the simplest variable expression there is, it's just x. Multiply both sides by x, we get x squared equals x, which has two solutions, 0 and 1. So what we did is, by multiplying both sides of this equation by a variable expression, we produced a new equation with a different solution set, okay? This potentially can happen whenever we're doing this, whenever we're clearing out these fractions. These are two different equations. However, any solutions to this original equation will always also be solutions to the resulting equation. So what this resulting equation will give us is potential solutions to the original equation. So we can multiply both sides by whatever variable expression, right, polynomial expression we want, as long as at the end we check all of our solutions, right? We consider them potential solutions until we go back and check them all to see which ones are actually solutions to the original equation. So hopefully that makes sense. From here on out, we're always going to check our solutions at the end and see what the actual solutions to the original equation are. All right, so here's another example. The first thing we're going to do is always rewrite this equation so that all the denominators are fully factored. That way we can easily find the least common denominator. So 4 over x minus 2. X minus 2 can't be factored. right? That's as simple, as broken down as it can get. So we're just going to rewrite that. However, this x squared minus 2x, I think I could factor that if these two terms for sure share a common factor of x. So if I take that out, I'm actually just left with x minus 2, and that's as factored as this is going to get. So this expression here factors into x times x minus 2, and that's as factored as it can get. And on the right hand side, we're going to leave that negative 2 alone, nothing to do there. So I've rewritten this equation so that all the denominators are fully factored. Now I'm going to use the same method I used in the first example, where I look at all the unique factors. In this case, there's just two, x and x minus 2. And I look at what's the most number of times each of these appear in any given denominator. Well, with this x, we have 0 and 1, so that's just 1. And with the x minus 2, we have 1 and 1, so that's 1. So the least common denominator is x times x minus 2. If you have a different method of doing this, that's awesome. If you can just look at this equation and tell that it's x times x minus 2, that's awesome. If not, you'll get there eventually. Really, we just need a method to find the least common denominator, so we can multiply both sides of this by it. Whatever method you have works for you, use that method. We're going to multiply both sides by x times x minus 2. So I'm going to erase this. This is just the scratch work I used to find the least common denominator. I put big parentheses here because everything on both sides of the equation is being multiplied by x times x minus 2. And again, I use the fully factored form of the equation as well as the least common denominator here, because I feel that it makes it a lot easier. We can see exactly what's going to cancel, right? For example, here, when I multiply this x times x minus 2 in this first term, the x minus 2's are going to cancel. I'm going to be left with x as well as the 4 that's already there. So I'm just going to have 4 times x. Here, when I multiply this x times x minus 2 to this term here, everything's going to cancel. The x's and the x minus 2's, and I'm just going to be left with that minus 8 that's already there, okay? Here, that negative 2, nothing cancels. We can think of this as being over 1, so when we multiply it in, we're going to have negative 2 times x minus 2. Nothing cancels. Now we have our resulting equation, right? We multiply both sides of the equation by an expression with variables in it. So this is our resulting equation. So all we have to do is solve this resulting equation for x, check all of those solutions we find, and then determine what the solutions are to the original equation, okay? So whatever method you have for solving this, it looks like it's going to be a quadratic. You can use whatever method you want. I'm going to go ahead and continue. I think I'll probably just try to fully factor it and find the solutions that way, right? Get 0 on one side, everything else on the other, that sort of thing. So negative 2x times x, let's distribute this in. That's going to give us negative 2x squared. Negative 2x times negative 2, that's going to give us plus 4x, okay? That's a plus. On the left-hand side, we'll just leave it alone for now, 4x minus 8. So now this is what we have. It indeed is a quadratic. So I'm going to continue. I'm going to get 0 on this left side of this equation. Move everything over to the right. So I'm going to add 8 to both sides. Okay, so the minus 8 plus 8 will cancel. Then I'm going to subtract 4x from both sides. And what's nice about this is it actually cancels on both sides. Plus 4x minus 4x, those cancel. Plus 4x minus 4x, those cancel. So now I have this 0 on the left-hand side of the equation. And on the right-hand side, I have negative 2x squared plus 8. Now I notice there's at least, there's a common factor between these two terms. What I'm just going to go ahead and do is divide both sides of this equation by negative 2. If I divide both sides by negative 2, well, 0 divided by negative 2 is still 0. So the left-hand side, nothing changes. But look what happens on this right-hand side. Negative 2 and negative 2, those cancel. Now I just have a coefficient of 1 on this x squared term, which I like a lot, okay? X squared, 8 divided by negative 2, that gives me negative 4. And now look how beautiful this is, because now this is a difference of squares. This can be factored. Let's draw a little arrow here. This can be factored into x plus 2 times x minus 2. Difference of squares can be factored x plus 2, x minus 2. So that means the solution set to this resulting equation is -2 and 2. We have two solutions to this resulting equation. So are these necessarily solutions to the original equation? Not necessarily. Now is when we have to go back in and check. So we're going to plug each number in, and what turns out that happens when we plug in +2 is that we get 2 minus 2, that's 0 in the denominator here. 4 over 0 is not defined. So 2 does not work as a solution to this original equation. Turns out that -2 does work, and if you want to write all that work out to check this, I encourage you to do that on your own. But 2 does not work. That is not a solution. So the solution set to this original equation is -2. X equals -2. Hopefully that example helped and made sense. We're going to do one more example to finish off the video. So before we move on to the last example of this video, let's summarize the steps we've been taking for solving these rational equations. So the first thing we always do is rewrite the equation so that all the denominators are fully factored. That way we can easily find the least common denominator and then multiply both sides of the equation by getting rid of all the fractions. Once this is done, we have an equation that we solve. We solve the resulting equation. Then we check the solutions to make sure they're actually solutions to the original equation. We may have extraneous solutions. So let's see if we can apply these steps once again to one final example. Since this is the last example, what I encourage you to do is go ahead and pause the video, pull out a pencil and paper, try this on your own, then press play to check your answer and compare your work with mine. All right, so I'm going to assume you're done at this point and you're just checking your answer. So again, what's the first thing we're going to do is we're going to rewrite this equation so that all the denominators are fully factored. So 36 over x squared minus 9 is actually a difference of squares. It can be factored into x minus 3 times x plus 3. Okay, so that's the left-hand side of the equation rewritten. And actually, this whole right-hand side of the equation is already fully factored. X plus 3 can't get factored down anymore. Obviously, 1 can't either. So really, it was just that one term in that denominator that needed to be factored, and we can just rewrite this whole right side of the equation. Now, all of the denominators are as factored as they're going to get, and we can identify the least common denominator so we can multiply both sides of this equation by it, okay? So hopefully, as you get more experience, again, you'll be able to just look at this and determine that the least common denominator is x minus 3 times x plus 3, and that's what we're going to multiply both sides of this equation by. But if you aren't at that point yet, what you can do is identify all the unique factors, which in this case are x minus 3 and x plus 3, and look at what's the biggest number of times each of those appear in any given denominator, and it's once for both of them. So that produces this. This is our least common denominator. Hopefully you're getting practice and starting to feel comfortable with that. So let's multiply through, and what we're going to see on the left-hand side of this equation is everything cancels. Super nice. So we're just left with 36. Right? When we multiply, the x minus 3's cancel, the x plus 3's cancel. We're left with 36 on the left-hand side of the equation. Beautiful. Okay, let's look at this term, 2x over x plus 3. So the x plus 3's are going to cancel, and we're going to be left with the 2x that's already there, as well as the x minus 3. So we're going to be left with 2x as well as the x minus 3. And then this minus 1, there's obviously nothing's going to cancel there, so we're just going to have the x minus 3 and the x plus 3. All right, so this is our resulting equation. We want to solve this. It looks like it's probably going to be a quadratic, so whatever method you feel comfortable using, you can use. I'm going to go ahead and start the distributing process on the right-hand side. So I'm going to copy down this 36, and on the right I have 2x times x, that's 2x squared. And then 2x times a negative 3, that's minus 6x. Here, I could FOIL this out, but look, where did this come from? This came from this. So I already know what it's going to be when I FOIL this out. It's going to give me x squared minus 9, right? We're going the opposite direction by multiplying this out. Hopefully that makes sense. So we have minus, and this is where we need to be really careful, this is a very common mistake, is we have minus x squared minus 9, but this is minus this whole thing, right? So what's going to happen is we're going to have minus x squared, but that minus 9 is going to become a plus 9. So make sure you be real careful with these terms and these negatives and making sure they get distributed properly. So let's go ahead and rewrite this out. What do we have now? We have 36 equals 2x squared minus 6x minus x squared plus 9. Now let's see what we can do from here. Well, I can combine some like terms, 2x squared minus x squared, right? Here and here, that actually leaves me with just x squared. So I have 36 equals x squared minus 6x plus 9. And now I'm actually just one step away from being able to try to factor this thing, hopefully, if I subtract 36 from both sides, right? Because the goal is pretty much always to get 0 on one side when we're solving these quadratic equations, remember. So subtract 36, these are going to cancel. 9 minus 36, so on the left hand side I'm going to have 0, and on the right hand side I'm going to have x squared minus 6x. 9 minus 36, so that's minus 27. From here you can use the quadratic formula if you want. I'm going to attempt to factor this. We have 0 equals, I think this is factorable, so let me just draw my little parentheses here. Okay, I know that this is a minus, so we need to have one of them as plus and one of them as minus. Now let's think of what two numbers multiply together to give me that negative 27, but add together to give me that negative 6. So let's think of factors of 27. We have 27 and 1. We have 9 and 3. I think that's actually going to work. Plus 3 minus 9. How can we double check it? Well, we can multiply this out and see if we get to here. We're going to get x squared minus 9x plus 3x. That's going to give us that minus 6x and then the negative 27 at the end. So it turns out that the solution set, let me draw a little arrow here. The solution set to this resulting equation is x equals, so we have two solutions, negative 3 as well as 9, okay? So these are potentially solutions to the original equation. We just need to go back and plug them in and make sure they actually work, okay? So when we go back and plug in negative 3, that's going to give us a problem. It actually gives us a problem here because we get 0, as well as here. Negative 3 squared is 9, 9 minus 9 is 0. Bunch of problems. Negative 3 is not going to work. Let's cross that out. Big hex, okay? Turns out that 9 is going to work. 9 is going to satisfy this original equation. If you don't believe me, go back and check it yourself. So the solution set to this original equation is just 9. 9 is the only solution to this original equation. So hopefully you got something out of this video, got some good practice, feel more confident with solving these rational equations. If you do, make sure to hit like. If you have any questions or comments, leave them below. Subscribe as well, but most importantly, keep flexing those brain muscles, and I'll see y'all next time.